utility of never enrolling. And given that it's further in the future, the sophisticate's waited longer, he's going to get less relative benefit, or he's going to lose less at time 2 from non-enrolling than he does at time 1 or time 0. He's going to end up paying less for the commitment device than he would in previous periods. Okay. All right. Let's move on to projection bias. So projection bias is a model of state-dependent utility. Let's see. I mean, we've used this phrase in a few contexts. Think of projection bias kind of all by itself. Don't confuse projection bias and state-dependent utility with the use of state-dependent utility in other contexts. Okay. So hopefully you guys remember from midterm 2, my utility from eating a hamburger today is going to depend on what state I am in today, whether I expected to eat today or whether I plan to fast today. So C1 depends on S1. And my utility from eating a hamburger tomorrow, so C2 is going to depend on the future, my actual state in the future, so whether I'm hungry or not, but also my expectations, whether or not I expect to eat tomorrow. And what I imagine my utility will be from eating a hamburger tomorrow partially accounts for the changing state, but not entirely, and that's where projection bias comes in. All right, so here's the general model of the projection bias, general form of the projection bias model. And in this case, if alpha equals 0, there's no projection bias. And you'll correctly predict how you'll feel in your future state. And then if alpha equals 1, you have complete projection bias, and you can't imagine feeling differently than you do now. And I need to change that slightly, but it's almost correct. Okay. What if somebody has both types of bias, present bias and projection bias? So if every day starting tomorrow is going to be cold, you want to order a coat. Did the professor talk about this example in class? Okay. This is actually one of my favorite papers. However, if today is warm, I'm still going to be willing to pay more for a coat that arrives tomorrow versus a coat that arrives in a week. So this initial cost is going to be more worthwhile if the benefit's not in the distant future. And it'll if delta is strictly less than 1, it'll also be discounted highly. There'll be the long-term discounting as well. But if there was a cold front today, I'll pay even more for a coat because I've just been recently reminded how incredibly unpleasant it will be to be without one in the future. And if it arrives tomorrow and I'm cold today, I'll pay the most. If it arrives in a week and I'm cold today, I'll pay more than if I'm cold, but less than if it arrives tomorrow. So the relative price that you're willing to pay if it's with warm tomorrow versus cold in 1 week depends on the relative strengths of your present and projection biases. And I thought you guys might have been, I think you guys were assigned that paper, but maybe not. But if not, then I'll write a little more detail in that slide. Okay. Sometimes it's hard to tell the difference between projection bias and hyperbolic discounting, i.e. present bias. So for example, a woman says she doesn't want an epidural during childbirth, but then when she's in labor and she's feeling the actual pain, her actualities are different from her expectations, and she changes her mind. And then the second example could be one's feelings about going to the gym, which you guys are familiar with. So how can you tell projection bias and present bias apart here? What test could you design? Something we talked about recently. Not in lecture, but in the review. Sorry? So a test to tell whether the behavior is explained by projection bias or. And how can you test if there's procrastination? So yes, what's an easy way to do that? How would you tell the sophisticate had projection bias or present bias? Yeah, no, you're remembering the right thing, but how is that not projection bias? Yeah, no, I mean, that's one reason I wanted to put this in here. So one of the easiest ways is to see if any proportion of the population you're looking at has a demand for a commitment device. And if there's demand for a commitment device, then which phenomenon is at play? Present bias, yeah. So projection bias, if you introduce a commitment device, there should be no impact.
But commitment device means someone paying to not use the epidural? Like, I will pay you to prevent me? That seems awful.
Or for instance, like, going to like a midwife, so that it's much harder for you to get to the hospital. I mean, it's if you believe that, well, not if you believe you're sophisticated. If you're actually sophisticated, it makes sense, right? But yeah. I chose to go to grad school instead of have kids, so I think you understand my preferences regarding that. Yeah, if the entire population is naive, then yeah, there won't be any demand for commitment devices. Yeah, and so you wouldn't be able to tell between present bias and projection bias.
So like for projection bias,
We have not assumed that we can. Yeah. I mean, so we're usually given what alpha is. Oh yeah. There's no, what we learned in this class, yeah, we have no sophisticate naive distinction when we talk about projection bias. So assume everybody knows. Well, you don't know when you have projection bias, but yeah, there's no difference between people that know they have it and people that don't know they have projection bias. You could, yeah. If you gave them the choice to go literally the second. Yeah, I mean, so the thing is you wouldn't be able to tell or test for present bias because there's no future period. So there's no way to measure beta or projection bias because there's no future. Okay. Alrighty. So present bias, projection bias, and preference reversals. It all comes together. Okay, so remember how preference reversals are our smoking gun for irrational decision making? Memorize that phrase. I mean, obviously, I haven't seen the exam, but that's just an easy thing to remember. Okay, so let's see. So we have reference dependence. That's going to be the case where we have the different sets of indifference curves for each reference point, and so intersecting indifference curves, multiple demand curves. So the comparisons of two options might change with the reference point. So preference reversal. With present bias preferences, people are not time consistent as they are with exponential discounting. So they might change their mind between periods. Another thing that's saying is people reevaluate their preferences each period, but the beta moves from all future periods here to these all future periods here to these all future periods here. And so that's why people might change their mind between periods and have a preference reversal with present bias preferences. And with projection bias, people don't anticipate what their preferences will be in the future, so they might change their mind when they realize what their true desires are. So, if I project that I want to eat an apple next week, but I get to that period and realize, no, I actually want some Cheetos, it could be the case that I'm going to have a preference reversal between this week and next week. Yeah, no, so I think that was a question that Avish asked. And so, yeah, if the entire population is naive, there's not going to be any demand for commitment devices. It's only if you have some proportion of sophisticates that you're going to see some change in behavior between when you don't offer a commitment device and when you do. Right. Just knowing all the pieces is good. Yeah. Any other questions? Okay. All right, so let me change to the other PDF, which I haven't mocked up in print-friendly LaTeX yet, so my apologies. Okay. Okay. All right, so this is reviewing a little bit what we just talked about. Okay. All right, so we just talked about this example, but so now we're going to talk about the same example from the 401k. So each day you're enrolled in a 401k, you get nothing at the end of your life. Each day you're enrolled, this is actually, slightly different example. So each day you're enrolled, you earn 3 utils at the end of your life, and each day you're enrolled in a 401k, you pay 2 utils and contributions. So essentially each day you're enrolled in the 401k, you pay 2 utils for 3 utils at the very end. Okay, but we still have delta equals 1 and beta equals 1/2 for the beta delta discounters. Okay. Thought I was writing this problem like the last problem. Okay, no worries. Okay. All right, so we want to talk about internalities. So remember, we want to make sure that we can apply present bias in particular to public policy, and one element of that is going to be calculating internalities. So often behavior has externalities, but I as an individual, don't care if you pay more for my health insurance if I eat Cheetos all the time. And so one way to cause people to internalize externalities is to tax the internalities that they incur as well, which are separate from the externalities. So obviously, internality, I'm going to die earlier if I eat a lot of Cheetos, and that's something that I actually care about. And so if you tax that part somehow, then that's one way that you can get behavior to change for both. That's better for both me, but also all of you who have to pay the externality of my bad behavior, or present bias behavior, not bad behavior. Judge not, lest ye be judged. Let's see. Unless you're Jonathan Gruber, in which case everyone else is an idiot. Nobody read that story. MIT economist, one of the architects of Obamacare. Oh, come on. Okay. All right, back to... Okay, so how do we calculate internalities? So we know that an exponential discounter, is going to act optimally, and in this case, he's going to have, let me see, he's not going to have any beta, and in this case, delta equals 1 for the exponential discounter, and so he's not going to discount any utilities of today or the future, and so he's going to weigh the cost of paying 2 today into the 401k against the benefit of 3 at the end of the 5 periods. On the other hand, a present bias discounter is going to weigh the cost of putting 2 in today to the 401k against the discounted benefit of getting 3 at the end of time. And so that's going to be beta times 3 because present bias discounters bias every period in the future equally. So it's going to be 1.5. And the difference between these two is going to end up being 1 minus beta times 3, and that's going to be the internality. And so 1 minus beta was 1/2 here, and so the internality is going to be 1.5. All right. Okay, so what if at time 1 there's an option to force yourself to enroll at day 3? Remember, this is a commitment device. If somebody else offers it, it's a commitment device. However, you can be, and it's an option, it's a commitment device, but if you are forced to do it, then it's a nudge. Okay, so if at time 1 you have an option to take a commitment device, so a naive, we'll assume full naive, believes they're going to enroll at day 2, so they don't care about this option at all, because that's what the exponential discounter is going to do. Sophisticate knows they're never going to enroll if left to their own devices. However, if the sophisticate buys the commitment device, they're going to end up enrolling at time 3. And so the naive is never going to pay for the commitment device because they don't believe they need it. The sophisticate, however, is going to have a value for the commitment device, and then that value is going to be the cost of the commitment device plus the difference in value between buying the commitment device and not buying the commitment device. And so the utility of buying the commitment device is going to be negative p, which will be the fee for the commitment device, plus 1.5, compared to getting a utility of 0 if they don't buy the commitment device. And so that's going to be the willingness to pay at time 1 for the commitment device for the sophisticate. All right, so we have the possibilities of enrolling at time 2 and time 3, and these answers depend on the numbers that are given. No need to remember a general result here. But what does this have to do with policy? So you guys didn't seem to talk that much about libertarian paternalism or asymmetric paternalism, but I've seen questions on 3 previous finals on this, and so just memorize the definition, and then the applications won't be too hard. Okay, so for asymmetric paternalism, make sure that a policy passes, well, the mode of operation, MO of asymmetric paternalism, is to make sure a policy passes a cost-benefit analysis. So if you see this, add up the changes in utility for each person in the population, taking into consideration whether they're present bias, naive, sophisticated, exponential, discounter, etc. Note that not everyone can be helped. Some smokers are rational smokers. If you don't get very much utility from living, it's not a suboptimal outcome to die early. However, with libertarian paternalism, make sure a policy helps some people without reducing freedom of choice. Again, you won't have a super tricky problem to work through, but yeah, do know this stuff just in case. All right, so Bayes' rule review. So I mentioned to my students that I would try to write out all the probability laws, and I probably have a couple more that I'll put in. The first rule is the law of joint probability, or definition of joint probability, and you can flip it around, and I'll put in the different variations, but that's one of the basic ones to remember. Remember, you can always flip around P, A, and B unless you're given the conditional probability. So you can switch P, A, and B unless you're given that you want to calculate the probability of a specific event A given B. Okay, PA is going to be called the marginal probability, and that's the formula for that. Just memorize this stuff because it'll come in handy. This is a really easy problem that you can invent variations to because it's just all calculations. And so if I were a professor, I might think about doing that. And then for Bayes' rule in particular, that's the formula that you need to remember, and then you can take the formulas above and substitute them in as necessary. Okay, all right, so let's do a Bayes' rule example. So if urn 1 has 3 red balls and 7 blue balls, and urn 2 has 6 red balls and 4 blue balls, if you draw a red ball from an unknown urn, what is the probability it came from urn 1? This is like a quintessential Bayesian probability problem from if you took a probability course in math department. Okay, so here we're not given any conditional probabilities, so we can choose what's A and what's B. Okay, so if we are given the conditional probability in this problem, so we want to make sure that we plug A and B correctly into our equation, but we'll use the equations that are here. So if we call A drawing a ball from urn 1, which is at the bottom here, the probability of A given B, that's A is exactly where we want it to be within this particular formula. Note that drawing a ball from urn 2 has probability 1 minus PA because there are only 2 urns. That's another rule that I should write in. So if there are only 2 events, or the sum of probability of all events equals what? 1, yeah. It's a really useful trick, but easy to forget in a moment. So drawing blue ball has a probability of 1 minus the probability of event B, and B is going to be the event of drawing a red ball, which is the given condition that we need in order to use Bayes' rule here. Okay, so we want to know the probability of A given B, and we just simply apply Bayes' rule. Okay. It's just there. I mean, Bayes' rule is so easy. Bayesian statistics, pain in the butt. But Bayes' rule and probability, when you know the probabilities, is amazing. Okay. All right. So here's an example of where I think the professor could make, like an application example, or something that you haven't seen before. Is a case where we have the probability of A, but say we need the probability of B in order to use Bayes' formula. So in this case, we could use the laws of probability in order to derive a formula for the probability of B. So we saw above that, for marginal probabilities, marginal probability, so probability of A is probability of A given B times probability of B plus the probability of A given not B times the probability of not B. So this is just, I guess by now we should all be familiar with laws of expectations. This is exactly what it is. So it's the value times the probability of that value occurring plus the other value times the probability of that value occurring. All right. And so just playing around with these formulas could definitely be something you haven't exactly seen before in public sector class. But as long as you memorize enough probability rules, you'll get there. Okay. Okay, so, and here's a further example. There's so many examples of ways that you can just tweak this problem a little bit. So imagine you'll play this game 1,000,000 times. So what do we know about independent probabilities? So if A and B are independent, what's the joint probability? Heard something. Sure. So if A and B are independent events, and so the probabilities are independent, what's the joint probability? So the probability of A and B happening, both. Yeah, so multiplying the marginal probability. The probability of A times the probability of B. So here, so this is with replacement for those of you who have taken probability. So in this case, it's going to be